notice down here it tells us that x dot y, the dot product of the two vectors, is positive if they form an acute angle. The dot product is negative if they form an obtuse angle. And if the dot product is 0, we say they're orthogonal. So let's just draw a quick little picture of that here. So if we have, let's say, x here and y here, then this would be the angle between them, an acute angle. And this would be the case where x dot y will be positive. If we now have, let me take a different color here and draw, let's say, a vector, I'll call it y prime, down here. In fact, this is minus y, actually, although maybe I'll make it a little longer. Okay, and so let's make this y prime, which is simply a negative multiple of y, the way I've drawn it. And so the dot product of x and y prime, since this is an obtuse angle, is going to be negative. And of course, if I take, let's take a third color here, I guess. If I take a vector like this, let me call this z here. No, let's call it y. Let's call it y double prime, just so I continue to use x and y here. So this is supposed to be, the way I drew it, a right angle. And so in this case, we would have x dot y double prime. That would be 0. And we would say that these two vectors, x and y double prime, are orthogonal. And so further, you should note that this would be true for all vectors, I call them y double primes, on this line through the origin. Everything on this line here would be a vector, which if I take its dot product with x, the dot product would be 0. Let me actually do one more thing with this picture here and with the dot product. Let me change this, the name of this vector, to p. Okay? So now everything on this line through the origin, through the 0 vector, is everything along here now. Every x on here is an x such that p dot x is 0. Every vector on this line is orthogonal to p, forms a right angle, and so p dot x equals 0. I'm going to call this set, and let me use this pink color again on this, and I'll put the h up here. I'm going to call this set h. And now you'll notice that all the vectors that form an acute angle with p are like this y. They all lie somewhere above this line h. And I'm going to call, so these are all the vectors here that satisfy p dot x positive. And I'm going to call this h super p. That's the set of all the vectors such that p dot x is positive. In fact, I'll even write it down here. Let's say h plus is the set of all x in R2, but I'm going to make it Rn in a minute, such that p dot x is strictly positive. And then the same thing works down here below the line. Everything down here is a vector for which p dot x is less than 0. So I'm going to call this set down here, whoops, that's supposed to be a minus sign there. I'm going to call this set here h minus. So what I've done here really is I've partitioned R2 into 3 sets. H, the line running through the origin, for which every vector in H is orthogonal to P, P dot x is 0. Secondly, the set above here, let's say quote above, it's above because this is the positive direction for P dot x. All the things up here, P dot x is positive, and all the things down here, P dot x is negative. And now let's notice that I did this in R2, but I could have done this in R3 just as well. I could have said, let me take a vector P in R3, and let me take all the vectors for which P dot x is 0. In fact, H, let me even write it this way. This is now I am going to use Rn here, and I'm calling that H. So H is the set of all vectors in Rn such that P dot x is 0. That would be in R3, that would be a plane through the origin. All the vectors perpendicular or orthogonal to P. And of course, it's hard to picture as soon as n gets bigger than 3, but we could still, analytically, we can still talk about and work with the set of all the vectors that are orthogonal to P. And we would also have this set here, all the vectors, such that P dot x is greater than 0, and that would be the same in Rn. And I didn't write the set down here, but the set of all vectors where P dot x is negative is here. And I used H because we're going to see this later on, so this is kind of a preview. The hyperplane, the plane in R3, the line in R2, or this set in Rn is called a hyperplane. And that's why I use the letter H. We'll be using that later on. And I used H plus because it's all the things to the positive side of the hyperplane. And this is all the things to the negative side of the hyperplane. And I guess I should maybe close this out by noting that the hyperplane doesn't have to, or the line, doesn't have to slope downward. It could be that I have my hyperplane looking like this. Let's draw our vector P down here, and then let's have our pink hyperplane, all the vectors x such that P dot x equals 0. That would be our hyperplane here, and this would be, since P is pointing this direction, this would be H plus, and up here we would have H minus. You might not be surprised to know that we are going to see a lot of these, because when I rewrote this as P, now you can see that if P is a list of prices, if it's a price vector, then the x's are all the activities, let's say consumption bundles for a consumer, or input-output vectors for a firm. In fact, let me take the firm and think of this as input-output vectors, either quantities that are inputs or outputs, outputs positive, inputs negative. P dot x would be the profit, the dollar value of the activity vector x, if this is the price vector, and this would be all the activities, all the input-output vectors that yield 0 profit. This would be all the input-output vectors that give us positive profit and negative profit. If it's a consumer, these would be these are the net purchases. So purchase is positive, a sale is negative. If these are the net purchases of a bunch of commodities, this would be all of the net purchase combinations that don't cost on net something positive, where you're spending the same amount as you're bringing in, spending the same amount for the things you sell as you're bringing in. You spend the same amount for the things you buy as you're bringing in revenue from the things you sell. That would be ones where P dot x is 0. So again, not a surprise perhaps that we're going to see these hyperplanes, which are sets such that P dot x is 0, and the two, what we call these is half spaces, again. And in fact, let me even write those down. Let's write those down just because we are going to use the terminology, and we'll see them again, even though I haven't developed the ideas in any detail. We call the pink line a hyperplane, or the pink plane in Rn, and we call the sets on each side of the plane half spaces, and you can see why half spaces. It's half of the space, half of Rn, in a sense. And so that shows us the relation between dot product, angles, acute angles, obtuse angles, and right angles, or orthogonality. And as I said, we will see those. So we will see those a lot. So the actual cosine, we, at least in microeconomic theory, we don't really use the cosine and what the angle is very much. In econometrics, you'll use it some more, but even there, you're using simply the sine of the cosine. That is, you're basically using whether the dot product x dot y is positive, negative, or 0. And so with that, I now want to move ahead to look at two of the things we just did a few minutes ago, the triangle inequality and the Cauchy-Schwarz inequality. So let's take this off, and then we'll come back and we'll look at those two inequalities. Okay, so now we are going to give proofs of a couple of inequalities, the Cauchy-Schwarz inequality and then the triangle inequality. These are fundamental inequalities in mathematics, and so these are ones that I think doing the proofs will kind of be instructive. I think it's kind of important for us to kind of do these proofs here, and maybe important for me to do and for you to see how we go about it. And so let's start with the Cauchy-Schwarz inequality, which we'll then use to prove the triangle inequality. So let's say we have here, this is really a theorem. So let's say it's a theorem, and it is the Cauchy-Schwarz inequality. And what the theorem says is that for any two vectors in Rn, what the theorem, the inequality, gives us is an important relation between the dot product, the absolute value of the dot product of the two vectors is always less than or equal to the product of the norms. Oop, there's supposed to be a y there. Let's take that off and make it a y. Here we go. Okay, so let's see how we can go about proving this. So first, if x or y is the 0 vector, the origin, then obviously both sides are 0. So both sides are 0, so of course this is less than or equal to this, so we have that. So now we are going to assume that x and y are both not the 0 vector, and we'll show that this inequality holds then as well. So how we do that? Let's define a new vector from x and y, and we're going to call this new vector alpha x, so it's a multiple of x, plus a multiple of y. Later on, actually not that much later on, we're going to see that these are called linear combinations of x and y. But for now, it's just a multiple of x plus a multiple of y where, so first, we're going to say alpha is the norm of y and beta is the norm of x. So if we have this, then what we want to look at now is I want to look at the norm of alpha x plus beta y squared. And so that is going to be, and now I'm skipping a few steps here. You can fill in the steps yourself, or you can go to our lecture notes where you can see the steps filled in. But it might be actually a good idea to try to do the arithmetic yourself first before you look at the lecture notes. So we have here 2 norm of x, norm of y, norm x, norm y, plus x dot y. Okay, so you do the arithmetic, you will get this. And of course, this side is positive because, certainly not negative because it's something squared. And actually it could be 0 because we could have x and y both not the 0 vector, but the alpha and the beta could make these 0. So this is non-negative. So let me just put that over here. This is greater than or equal to 0. And now these are strictly greater than 0 here because x and y are both not the 0 vector. So I have positive, strictly positive, strictly positive, strictly positive, strictly positive. This could be negative. So this is greater than or equal to 0. This is actually greater than 0. So that tells me that this has to be greater than or equal to 0. Also, this is positive. This has to be greater than or equal to 0 to make this greater than or equal to 0. So that tells me that the norm of x times the norm of y, I can take this to the other side of the equal sign, or the inequality. This is greater than or equal to minus x dot y. Okay, so now I'm going to do almost the same thing. I'm going to have alpha equal to the norm of y again, and I'm going to have beta equal to minus the norm of x. Then I'm going to get exactly the same thing. And so let me just do dot, 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 dot. Exactly the same thing, except the part in parentheses is going to be norm of x, norm of y, minus x dot y. So again, it's the case that this is greater than or equal to 0. This is positive. So that means that this has to be greater than or equal to 0. But now that means that the product of the two norms is greater than or equal to x dot y. So I have, therefore, this is greater than or equal to x dot y. So I have that the product of the norms, so let's now gather these two results together, and I have that the product of the norms is greater than or equal to this number, and it's negative. Well, in fact, let's write that. This is greater than or equal to the larger of the two numbers. If this is negative, that's positive. And so this is greater than or equal to both of them, so it's greater than or equal to the positive one. So this is greater than or equal to the maximum of x dot y and minus x dot y. And of course, the maximum of a number, and it's negative, is just the absolute value of that number. And so what have I got? I have that I actually have that this is greater than or equal to, it's not equal to the maximum, of course. It's greater than or equal to both of these, and that means it's greater than or equal to the maximum, which is the absolute value of the dot product. And of course, that's just what we wanted to prove. We wanted to prove that the product of the norms is greater than or equal to the absolute value of the dot product, and that's exactly what we have. So we've just completed the proof of the Cauchy-Schwarz inequality. It's a useful inequality that we will see some occasionally, but it's perhaps most important for us because this enables us to prove the triangle inequality straight away quite simply. So we'll take this off and then we'll give the proof of the triangle inequality. And I think that'll be it for part 2 of our Euclidean space lecture. So let's do that. Okay, this is going to go. Okay, we're back here now, and you notice that I've put back on the screen here our dot product definition and the theorem about the dot product properties, because we're going to use one or two of the properties in the theorem here in our proof here. So now we're going to do a theorem called the triangle inequality. And of course, what that says is for any two vectors in Rn, the norm of x plus y is less than or equal to the norm of x plus the norm of y. Proof. Let's look at the norm of x plus y squared. So that is equal to x plus y dot x plus y. That is equal to, in fact, if you look at dp6 over here, the sixth property in our theorem, that tells us that this is going to be x dot x plus 2 x dot y plus y dot y. Okay. That is going to be less than or equal to, first of all, note, well, I'll put an equal here first. This is going to be norm of x squared plus 2 x dot y plus the norm of y squared, but 2x dot y is less than or equal to 2 times the absolute value of x dot y. So let's put less than or equal in there. And that's just because the nature of the absolute value of a number. But now, notice that we can now apply the Cauchy-Schwarz inequality to this. And that will tell us that this is equal to the norm of x squared, less than or equal, because here I'm going to put in the norm of x, the norm of y, plus the norm of y squared. And of course, everything in here is a real number. So that's a number squared, but it's a number. A number, 2 times this number and this number and this number. Well, this is just a quadratic expression, which is exactly the norm of x plus the norm of y squared. So what I have here is, this is non-negative because I'm squaring something. This is non-negative. I'm squaring something. And so if I take the positive square root of both sides, I have, because less than or equal, these two inequalities here, voila, we are done. A very simple proof. So we wanted to prove, very simple proof, but of course made simple by the fact that we were able to use the Cauchy-Schwarz inequality at this step here. So this gives us a pretty good foundation, I think, on the norm of a vector, the distance between two vectors, the dot product of two vectors, and its relation to the angle between vectors. And we saw how that was related to hyperplanes and half spaces. We could come back and see those again. And now the Cauchy-Schwarz inequality and the triangle inequality, which you'll recall the triangle inequality showed up, well, the triangle inequality that we proved here is the triangle inequality for the norm, but we also have basically the same inequality, the triangle inequality for distance, which, as I've pointed out, you can obtain from N4, the triangle inequality for the norm, with some straightforward arithmetic, straightforward algebra. So that does it for part 2 of our Euclidean Space lecture. And when we come back, we will do part 3. So that's it for now, and we'll see you next time.